Good morning, champs. Today, we solve our first real challenge frame problem. This one looks much more complicated than the examples before because several load types appear at the same time. We have a point load, a horizontal point load, a uniform distributed load, and a triangular distributed load. But the main message is simple. We do not need a new method. We only combine the tools we already learned. First, we identify the load types. The top beam carries a uniform distributed load of 4 kilonewtons per meter over a length of 2 meters. The left column carries a triangular horizontal distributed load with a maximum intensity of 6 kilonewtons per meter. In addition, there is a vertical point load of 4 kilonewtons and a horizontal point load of 3 kilonewtons. Now we replace the distributed loads. The top load is rectangular, so its equivalent force is the area of the rectangle. 4 times 2 gives 8 kilonewtons. Since the load is uniform, this equivalent force acts at the center of the top beam, 1 meter from the left side. Next, we replace the triangular load on the left column. The equivalent force is the area of the triangle. 1/2 times 6 times 2 gives 6 kilonewtons. Because the larger side of the triangle is at the bottom, the equivalent force acts 1/3 of the height from the bottom. That gives a distance of 2/3 of a meter above support A. Now we draw the clean free body diagram. The distributed loads are gone. Instead, we have only point forces and support reactions. The unknown reactions are AX, AY, and BY. We start with horizontal equilibrium. Solving gives AX equals -3 kilonewtons. The negative sign means the actual reaction at AX to the left. Next, we take moments about point A. Counterclockwise is positive. The reaction BY creates a counterclockwise moment. The horizontal point load also creates a counterclockwise moment. The triangular distributed load creates a clockwise moment. And the equivalent force of the uniform distributed load also creates a clockwise moment. Notice that the vertical point load does not appear in the moment equation because its line of action passes directly through point A. So its moment arm is 0. Solving gives By equals 4.5 kilonewtons. Finally, we use vertical equilibrium. Substituting By equals 4.5 gives Ay equals 7.5 kilonewtons. The final reactions are Ax equals -3 kilonewtons, Ay equals 7.5 kilonewtons, and By equals 4.5 kilonewtons. A quick vertical check confirms the result. The upward reactions add to 12 kilonewtons, and the downward loads also add to 12 kilonewtons. The key lesson is that the problem looked difficult because many things happened at once. But nothing new actually happened. Replace the distributed loads, draw a clean free body diagram, apply equilibrium, and check the result. That is the same workflow again,